Foundation and Applications of Implicit Function Types, and its joint work with Olivier Blanvillain, Fengyun Liu, Aggelos Biboudis, Heather Miller, and Sandro Stucki. So let's talk about context. Well, let me do this. Let's talk about context. Context is what comes with the text, but is not in the text. And context is really all around us, whether we talk about the current configuration, the current scope, the meaning of an operation on a type, the user on behalf of which an operation is performed, the security level in effect, and so on and so on. All of these are different manifestations of context in a program. And the traditional story, how we express context, is actually not so great. Usually, people just used to use globals for that. And globals, they are very rigid when they're immutable, and they're terrible when they're mutable, because then essentially you exchange a context dependency for a timing dependency, and we know that is a recipe for disaster. Other terrible ways to express context are the so-called monkey patching, where essentially you inject things into the root object of your class hierarchy, and slightly less terrible ways to express context are the dependency injection frameworks, which are nevertheless quite bulky and difficult to deal with. Examples are Spring or Juice. So as functional programmers, of course, we know we have it much better. Parameterize all the things, that's the functional dogma, right? And functional is definitely good. So that way we can, by just expressing context as parameters, we can have no side effects, we can be type safe, and we have very fine-grained control what we want to pass where. But sometimes it's actually too much of a good thing. You tend to drown in a sea of parameters, most of which hardly ever change, and that's repetitive, boring, and prone to mistakes. So a more direct approach would be to simply say, if passing a lot of parameters gets tedious, leave some of them implicit. And that means we trade types for terms. So we provide a type of a parameter and have the compiler synthesize a term for the type. So that's the meaning of implicit parameters. The ground rules are, if you do not give an argument to an implicit parameter, one will be provided for you, and eligible are all implicit values that are visible at the point of call, whether by an import or by a definition. And then, if there's more than one eligible candidate, a most specific one is chosen according to some rules, and if there's no unique most specific candidate, an ambiguity error is reported. So that's essentially the basic rules that we have in Scala. And the last 2 points are really the same rules as for overloading resolution. If you have several overloaded methods, you pick a specific one, and if there are several ones, then it's an ambiguity error. And implicit parameters used that way have quite a lot of quite diverse use cases. They can provide evidence for properties, set configurations, inject dependencies, model capabilities, implement type classes, and establish context in a very general way. And so it's no wonder that implicits are really ubiquitous in the Scala ecosystem. So here's a graph of the first top 120 projects, Scala projects that use. And of those projects, 94% use some form of implicits. So it's fair to say that implicits are really used everywhere, and I would actually go a little bit further and say, if there's one feature that makes Scala Scala, it's implicit parameters. Just as I would also say, if there's one feature that makes Haskell Haskell, it's type classes. And in fact, implicit parameters can model type classes. So here's how you would do that. A type class is just a trait, so a type definition, and an instance of a type class that's just an implicit value that provides a value for that trait. And instances can also be conditional. So for instance, the lists are ordered if and only if the element types are ordered. So you get all the power of type classes with implicit parameters. It's really the same thing. But implicit parameters can actually do more than what type classes do, because they give you a very fine-grained way to establish contexts. So here's an example that actually Nadia proposed to me originally, a conference management system. So in a conference management system, you have a rule that an author should never view a review of their papers. So if there's a conflict between the viewers and the authors, then you shouldn't be able to view the paper. So the way that's implemented here is in the score function, which says, well, if the viewers have a conflict with the authors of the paper, then you will get a generic -100 value for the score of the paper, and otherwise you'll get the real score. But of course, getting a score of a paper is just one step. You shouldn't also be seeing what the score of a paper is in an indirect way. So for instance, the view rankings function that ranks the papers also needs to essentially hide the papers that have a conflict, and it does that by essentially also passing the viewers to the score here that is the function called by sort by. So since score needs a viewers parameter, so does view rankings, and that way you bubble up the parameters all the way to the root where actually the real viewers get established. And that gives you, as I said, very fine-grained control, because one thing you can do, for instance, is you can have a delegate function that has a query from viewers to some type T, and that wants to delegate that query to a person P. So what you do is you run the query with a new viewers parameters that just adds P to the current set of viewers. So you have one additional viewer in the set, and that means you can have, for this particular sub part of the computation, you have a different set of viewers than for the other parts. So all this is very nice, and what you save with the implicit parameters that you don't have to pass all these viewers around everywhere, that's handled by being implicit. But things are still not ideal, because after all, doesn't it get boring to write all these implicit viewers parameters everywhere? You might say, well, here now for writing these things a couple of times is not so bad. But if we want to scale up these things, for instance, to the current or next Scala compiler called .c, then there we find we have more than 2,600 occurrences of the implicit parameter ctx:context. Wouldn't it be nice to get rid of them? And in fact, we can, and that's the new things that I'm describing in this talk. It's called implicit function types. So to get to implicit function types, let's massage the definition of, let's say, view rankings a bit. It used to be a method with an implicit parameter. I just want to make it explicit now with a right-hand side, which is a lambda, an anonymous function. So it gets a viewer's parameter, and it does the sort by score. And the parameter is implicit. So an interesting question is, well, what's the type of this lambda, of this function value? In current Scala, it's just a normal function from viewers to list of paper. So we forget about the implicitness of this function. And all I'm proposing is to say, well, from now on, it will be an implicit function type, implicit viewers to papers. Well, of course, that's just a name. So what are the rules that govern these implicit function types? They're actually very simple. They're just two rules. The first one is that implicit functions get implicit arguments just like implicit methods. So if you have a value of an implicit function type and you have a matching implicit value A, then just using the name f would expand to f of A. And the second rule is that implicit functions get created on demand. So if the expected type of some body B is an implicit function type, then the body B will be transparently expanded to an implicit closure that takes an A into a B, because the expected type is an implicit function type. So that's the two rules. So with those two rules, we can now reformulate our conference management system as follows. We can say we have a type viewed of T, which is an implicit type function from viewers to T. And then our score function would take a paper and it would give you back an integer, but not just any integer, but an integer that is viewed by someone. So being viewed is an important part here. And the body of score would be exactly the same as before. And the same thing for the other functions. So everywhere I just say it's viewed, and the implicit parameters then get threaded through the program automatically. So where previously we traded types for type arguments or terms, now we go one step further and we trade types for the former parameters. So by specifying the type of an expression, we can provide a very general way a context for that expression. So we add further parameters, which is essentially the essence of context. That's the abstraction over contexts. And those types, they can be declared directly, as in the example, but they can also be inferred with local type inference. So in the end, this is pretty powerful. Are you confused so far? No? All clear? Well, maybe not. So let's try to be a bit more precise with the formalization. So what we have here is a formalization of the implicit function types that I've shown you so far. What we have here is essentially an implicit version of system F. What we have are variables, functions, applications. And what's interesting here is the functions are curry style, so no type is given. The type is given later in a let. So essentially, in the end, I define these functions by name as in a let, and there I provide a type for the let and a term, and then the body where the function is visible. So if you want to translate that to programming languages, think Haskell. So for a Haskell top-level function, you would give the type, and you would give the term, and the type itself, the lambdas, wouldn't carry any parameters. So that's, I think, the closest approximation to that. So what are the types? Types are type variables, function types, and those two form the so-called restricted types. I'll explain in a second why that is important. And then our full types are the restricted types plus implicit function types, which I write with a question mark, arrow T, plus polymorphic function types because we want to model system F. And the typing rules, they are bidirectional. So they are synthesis rules, which I write with a right arrow, and checking rules with a left arrow. So synthesis rules means the type is computed from the term, and checking rules is that the type is given from the outside, and I just need to check that the term has that type. And unlike other bidirectional systems, like for local type inference, what we will see here is that actually every syntax construct has only one of these two forms. So it's always either checking or synthesis, but never both. So, okay, so let's have a look at the rules then. Let's start with the rules for functions. So lambda xt is type S to T, if assuming x is type S, T is type T, and that's a checking rule because somebody has to tell me what the parameter type is. On the other hand, for the application, T1 needs to be synthesized, and once I know the type of T1 of the function part, I can run the argument in checking mode because I have the expected type. Okay, so those were the rules for lambda abstraction application. Let's have a look at the implicit version. They're actually exactly the same, so you see with the preconditions, except that there's no syntax. Well, of course, they are implicit, right? So I don't write these lambdas, I don't write the arguments. So what you see here is that if a term has an implicit function type, then the precondition would be the same as if the term was a lambda, an implicit lambda. The variable y here that I generate, they are form a different alphabet from the variables x, so they are essentially system-generated implicit names. And for the implicit application, I have, well, if T has an implicit function type, and I have a so-called query operator that has this thing, so an implicit query is successful, then T will also have the result type of T. So I eliminate the argument, but I do that without any argument syntax. The argument is implicit. Okay, so that was function applications. Variables are pretty straightforward, so that's just the usual var rule. It's actually a synthesis rule, and so is the query rule for the query operator. So if somebody says, well, give me an implicit value, then any y here, any of these implicitly generated parameters would match. So this system doesn't, in those rules, talk about ambiguity. That's essentially another concern. We just say, give me anything that you have in here. Okay, finally, the rules for let. So they are what you would expect. If you have here let x t1 equals t1 and t2, then t1 is computed in checking mode. I have a type for it, and t2 in synthesis mode. And for implicit lets, so if I just define an implicit value, I do the same thing, except I generate a fresh name for this because the name of an implicit value doesn't matter here. So if I put it all together, that's my type system. That's all the rules you saw. except for I haven't handled the polymorphic rules, which are the same as for system F. And there's one new rule that I haven't covered yet, and that's the stitch rule that you see here at the bottom of the slide. So the stitch rule says that if you can compute the type of something in some synthesis mode, then you can switch the arrow and assume that it also has this type in checking mode. And importantly, that's the rule that only works for restricted types. So restricted types are types, just function types, not implicit function types, not polymorphic types. So why does it only use for restricted types? It's because we essentially need to be clear where we create these implicit functions and where we eliminate them. So what the stitch rule essentially forces us to do that at the leaves of the proof tree, I eliminate all implicit function types, and at the root of the proof tree, if the expected type is an implicit function, I generate the implicit closures. And I don't want to oscillate and do that because the two rules cancel each other out, so I don't want to oscillate because that would give me indeterminate behavior. So that with that rule, everything is properly kept in its place. Okay, so what that gives me is, I said, an implicit version of system F. So we can make that clearer by translating it to system F. So here you see the translation. It's a type-preserving translation. The type are preserved in the sense that if I have an implicit function, I map it to a normal function, and otherwise they are all the same types. And the terms, as you see here, the gray part is just a translation to system F. So it's just a homomorphism here overall. The interesting parts are in the implicit introduction rule, where you see here, if I have an implicit function type, I will generate a lambda of the translated argument types. And on the other hand, if I eliminate an implicit function type, then I will create an application. Okay, so that was the theory, and I hope to have convinced you that the theory is really very, very simple. It's basically just lambda calculus, system F with a little twist and a type-preserving translation. So what can I do with it? So I actually believe that it's almost unlimited. As we gain more experience, we will find more and more applications of this. But some applications people have looked into already are in the paper. So there's the builder patterns, readers, tagless interpreters, free structures. And there have also been some other papers, notably one about algebraic effects at the last Scala symposium. So you can do, if you add these things with continuation monad, then you can do algebraic effects in a very, very nice way. One thing you can do, of course, is reading contexts. So there, I think I should discuss comparison with the reader monad, which is essentially another way to do reading in a way that doesn't make all these parameters explicit. So the reader monad, like implicit function types, allows abstracting context into a type. But of course, it forces you into monadic style. You have to write everything in a monadic bind, in a do notation, a for notation in Scala. And that's much more heavyweight than implicit functions, because implicit functions, you just keep direct style. There's nothing that you need to do to compose your programs together. And the other important observation here is implicit function types compose really well, whereas monads, as we know, do not. So for instance, just to get started, if I have an implicit function type of an implicit function type, so from A to B to R, and I have another one where I swap the B and the A, then those two types are actually compatible. I can have a value of one type and I pass it to an argument of another type, and it will all be handled transparently. If I do that with monads, I have need already do some fairly acrobatic monad transformer code to actually get from one to the other. With implicits, it's completely transparent. So I believe in the end, monads really are about sequencing. There's an important sequencing control aspect. So to use them just for passing context is overkill, and gives you a lot of problems, both performance-wise and compositionality-wise. Okay, so I think I have a little bit more time, so let's just do an encore. One other example in the paper was the builder pattern. So a builder pattern is a curious thing, and it comes actually from imperative programming. So It's quite popular in languages like Groovy and Kotlin, which have native support for these things. So essentially, it's a DSL for building things. So you see here, we build a table with rows, and rows have cells. And the question is, well, how does that work? If you know a little bit of Scala, then you will see that these things really, there's a semicolon between them implied by the line. And so there must be statements with a side effect. So what these things then do under the hood is that a cell would essentially add itself to the enclosing row, and a row would have to add itself to the enclosing table. But the question remains as well, how do I let the row and the cell know what the enclosing table or row is, respectively? It has to know to what other things it needs to add itself. So here's a way to write that. So let's start with table. So table would say, well, it has an initialization code. So that's the initialization code. This thing is just an argument to table. And what the initialization code needs to know is, well, what table does it, what's the enclosing table? So we pass that as an implicit parameter. We create a new value of that parameter. We pass it implicitly to init, and we return the table. Okay, so what a row then does, it also has an init method, which is the cells. So the cells need to know what row they add to themselves to, and the row needs to know what table it adds itself to. So let's create a new row, call init, and add the row to the enclosing table here. And cell then would just add itself to the enclosing row. So if we look at the original example then, so essentially here's the secret, here's the expansion, what implicit function types would do. Every time here, when we have this, we would create a new table. To pass into the table object, row would create a new lambda for these things, and then essentially for every time we call row or cell, we pass the enclosing structure to the enclosed one. Okay, so I think I'm out of time, so let's just quickly do related work. Of course, I mentioned already type classes. There's also a thing called implicit parameters in Haskell, much less popular than type classes, and somewhat related to what we have here, but details are different. Modular implicits in OCaml is a fairly recent proposal, which is very similar to implicit in Scala. Aggelos implicit instances are also similar, and actually they do have something which is corresponds quite closely to these implicit function types. There are also other formalizations, notably implicit calculus by Olivier, Schreibers, Wadler in several versions, and there's also a version by Rouve. The implicits are implemented in Scala and in the later Scala version Dotti, so you can use them right now. And of course, that's a big effort, so many people were involved on that, and I won't mention them all. But thank you for listening, and happy to take questions. Thanks.
So I have a basic question. So you're saying that the introduction of these implicit function types is a new thing in Scala? They weren't there before at all?
That's right.
So how before did you, if you have, say, you define some function that has an implicit argument, how would the caller of this function know that, at the call site, how would you know that there was an implicit argument to be generated if it wasn't in the function type?
So in Scala, we have methods and we have functions. Methods are things in objects,
and
functions are real values.
Okay. You're talking about the closures themselves.
And only methods could have implicit parameters, but not function values. So now both of them can. Thanks for the question.
I was intrigued by your comment that these implicits are more lightweight than monads, and that monads are essentially sequencing. We know that monads don't compose unless you have a distributive law which tells you how to resequence things. So I'm wondering if you have any comments about compositionality in relation to your implicits.
In relation to, you mean compositionality for the implicits?
Well,
or?
I'm wondering whether you can see the building of a larger environment as the composition of building smaller environments, whether you can express it in that kind of way, whether you have a good composition rules for these.
You do have good composition rules for the implicits, yeah. I could only sort of mention that in passing to say, well, to start with, they commute. But I think we are only scratching the surface here. But so far, they were holding up quite well in these things. So.
Okay, thank you.
So in your table row cell example, I like the end result, but the idea that row and cell are side effecting operations just bothers me a little bit. And I was wondering, could you separate out that bit into something that somehow implicitly, generically receive the result of any expression statement, so that you still get your simple row and cell constructors, and you just the table initializer function says that anything any expression statement result just gets passed to this handler function. So that you get kind of the best of both worlds.
That's an interesting thought. I have to think about it, but it looks plausible. Yeah.
Okay.
It was just this one was sort of. I didn't come up with this. Somebody challenged me and they said, "Hey, Kotlin has this cool thing, and I heard you have these implicit function types. Can you do that?" And it turned out I can't do that. But I agree. It's imperative and therefore maybe a bit dubious. Yeah.
Martin. Can I think of implicits as follows, namely as the inverse of the following operation, I mean erasure operation. So there's the explicitly typed on, all details there. And then you say in the syntax, I'll give the programmer a possibility of leave out certain things. And that's the erasure operation, right? And then you say, okay, I'll synthesize the missing parts if they're unique in some fashion. I mean, if they're semantically unique. Is that a way of...
That's an interesting thought, to think of them as reverse erasure.
Well,
I hadn't thought about it, but yeah.
Okay, let's stipulate that.
Yeah.
So that means like there's a magic step involved, right? So the compiler does some kind of magic inference. And so two questions. First of all is like in some cases you have ambiguity, right?
Yes.
I mean, possible ambiguity, so you have to flag that as an error.
Yep.
And the second part is that when robust on the program changes. So I'm a programmer, I'm doing these things implicitly, I'm changing something, I'm inlining something. And will the inference then guarantee that it doesn't just, infer some very, very complicated, very expensive code and previously was very fast?
Good point, yeah. So it actually turns out that the details of the rules matter a lot. And in the Scala context, I think I can say with confidence, yes, we have the right rules. So it really, there is no surprise what it gets. But it's sort of, you have to get the right rules with iter expansion and things like that, about which I really haven't talked much. One caveat is that I believe that this thing works really well with local type inference. So you trade types for terms, and if your type inference is global, then you're on much less solid ground what types you get. So if then those types can generate terms, maybe that's a bit too much of implicitness. So I have the impression that these context-dependent implicits are a really good match for type systems that use local type inference, where you still have a pretty good control where the types come from, and that for type systems with global type inference, it's less, it's maybe too implicit, and I believe that could also be an explanation why the implicit parameters in Haskell haven't really caught on. But that's a speculation.
Last part of my second question. So system F is an absolutely terrible type system for type inference. And you're doing a lot of inference, but you have to signal somehow. The program apparently has to signal, like we've seen in some type inference algorithms, like I'm not just inferring things that's too difficult, so I have to give sort of like compiler directives. So please synthesize, switch direction. If I understand that right, that's the reason you have these.
That's done automatically. Basically, the switch rule just says if you have a type judgment and the expected type, which we have because we have local type inference, so we always have an expected type, which can have holes, but we have a shape of an expected type. If that's an implicit function type, then unconditionally generate an implicit lambda. And on the other hand, it says, well, if you have a variable, if you take it from the environment, and that has an implicit function type, unconditionally eliminate it by looking for an argument.
Thank you.
All right, let's take Martin again.
Okay.